Beautiful. We love to see it. All right, let's go ahead and get this shindig started. I'm just going to put my slides into viewer mode. Slideshow. Cool. Share that screen. Beautiful. You should all be seeing some kind of intro slide. Okay, cool. So welcome everyone to our PyHC Spring 2024 meeting. Today's Monday, March 11th, and this will go until Thursday, March 14th. It's going to run 9 to 11 each day, Mountain Time on Zoom here where you are now. And each day I'll send out a reminder an hour before the meeting with the Zoom link reattached just in case you forgot it and so forth. Okay. Raise your hand if you don't know what PyHC is at this point. Some people might be new on the call. I think you might know, Stuart. Okay, I'm going to just blaze through this slide real quick. I always include it just in case we have someone new. In case you're not super familiar with the effort here, we're basically a community base for performing heliophysics research in Python, specifically open sourced. So the goal of this whole group has been to help establish standards and processes, share lessons learned among developers, reduce incidents of duplicated effort, as well as improve interoperability between all of our packages, identify opportunities for future collaborations and different ways packages can connect together. And yeah, that last point I already mentioned. So twice yearly, we come together for these kind of meetings, either in person or virtual. Just a heads up that probably the fall one I'll do in person since we did this one virtual. And it'll be here in Boulder. Dates TBD, but assume after Dash. So the goal of these meetings is to update the community on our package development, discuss relevant topics like the PyOpenSci partnership we're seeing, FEP1, things of that sort, and continue to find further areas for collaboration and apparently not integration. So we have bi-weekly telecons and schedules allowed, and then you'll see us at a lot of the other meetings around throughout the year. And you'll see on the last day a reminder for upcoming meetings, including our summer school. So if you have not registered for our summer school, it's going to be here in Boulder, and you should come or attend virtually. It's free, $3.99. All right. So meeting overview. This is already our 11th PyHC meeting, which kind of seems wild. It feels like we haven't been around that long, but here we are. Like I said, all meetings are going to run for 2 hours each day, 9 to 11 on Zoom. To be covered during this meeting. Today is going to be all of the core project updates, not really project overviews necessarily, just actual updates on what's happened since our last meeting. Tomorrow, we'll have a couple of presentations on some new NASA HTM projects that have been funded recently. Sean's going to talk about science platforms coordination, that group, what's going on there, and so forth. And then we'll have a discussion about a new heliophysics software search interface that myself and several other people on this call are in the talks about putting together. Wednesday, we'll go through FEP1, have our final discussions, do voting, things of that sort, and then talk through the next steps with the PyOpenSci partnership. That's coming along, and we really want to kick it off and hit the ground running on that. Thursday, I've set aside some time for unconferences. So that's the one day that we won't record. A part of our Zoom sessions is during those unconferences. We'll still have notes and so forth for big ideas we want to take away from that. And then we'll do wrap up. So normal housekeeping, again, if there's a presentation going on, try to remember to mute yourself or I will mute you. If we're having a discussion, that's a different case. So all documents and presentations with this meeting, as well as the agenda, are going to be on the PyHC drive and or on the meeting's website itself. So if you're ever trying to re-find the Zoom link or the agenda, this is probably the easiest spot to go to. And I'll paste the first 2 bullets into the chat here, but as usual, we'll have a general meetings note, Google document that anyone can add information to. And then for the unconferences on Thursday, I started a spreadsheet. Please add all your ideas there. Rebecca, you sent me a nice list. I'll add them to that spreadsheet for you already. But everyone else, please add your ideas. And then I think Wednesday, probably towards the end of our Zoom meeting, I'll send out a link where you could go and vote for which ideas you want to have discussed most. So that should be all from me, and we can go ahead and continue along. So first up should be Senpai, actually.
Yeah. Let me share my screen. If I can find the share button.
They highlighted
yes, it's right. It's right in front of me. Okay. Okay. Can people see that?
Yeah.
Great. Okay. For some
Everything?
reason, it wants to hide the chat, so I cannot see that, but whatever, that's fine. Okay. Yeah, thanks, Julie. Yeah, so my name is Will Barnes, and then I'm going to be giving this presentation with Stuart Mumford, and we are the two of the lead developers of the SunPy project. So if you don't know what SunPy is, very briefly, the idea is that it provides a sort of a toolbox for analyzing solar data. In the past, our focus has sort of been on specifically solar image data. So we provide things like data search, data containers for sort of basic data formats, including image data and time series, and as well as a sort of toolbox for coordinate transformations, which I'll talk a little bit about in a bit. So this is just, I'm not going to really go over in detail every part of SunPy. This is just kind of a brief update on what's been happening in the package and in the project as a whole, kind of since the last PyHC meeting. Okay. All right, so we had our 5.1 release back in November of 2023. So this is gonna, I think this was post the fall PyHC meeting. So I'm gonna kind of cover a few of the new features that were introduced in version 5.1. Based on our release calendar, we're going to have a version 6 release coming May of 2024. So hopefully we'll have an update at the next meeting on what exactly goes into that. So very briefly, so SunPy is sort of refers to the actual Python package that I was talking about previously, but also the SunPy project is sort of the umbrella organization that helps to manage the development of that package, as well as the system of affiliated packages, which I'll talk a bit about. And one of those is a new package called SunKit MagX, which is a successor to PFSS Pi for doing potential field extrapolations. We'll also give a kind of a brief update on the new SunPy package template. Actually, Stuart's going to talk about that, and then the kind of accompanying packaging guide. And then I also wanted to mention that Julie mentioned this in the intro regarding the kind of PyHC PyOpenSci partnership, but SunPy has also recently been accepted into PyOpenSci. So we have a partnership with them, and then there's this link here that's an issue on the PyOpenSci GitHub repository. You can actually see the whole review that we went through. Actually, Nabil Frage was the one who kind of spearheaded that, and we've recently been accepted. And probably the biggest update or the biggest change that comes along with being a partner with PyOpenSci is how that affects our affiliated package system. So we have in the past, we've had a review, kind of an internal review process for accepting affiliated packages into the SunPy project. That process will now be managed through PyOpenSci, as opposed to it being a process that we manage only by ourselves. And so that is that overhaul is ongoing. We haven't actually figured out how that's going to work. Yeah, I should also just mention that all these slides are available at this URL at the bottom of the page. So if you go to this link, it'll stay up there. They'll stay at the bottom of the slides the whole time. Then you can
I
click
just
all of
put
these
it in the
links.
Zoom chat and in Slack if people are in either of
Oh,
those
great.
places.
Awesome. Well, that makes it even easier then. Yeah. And then you can go and see all there's an accompanying repo for all these slides too. So you can take a look at them later. Okay. All right, so version 5.1. So this is just some kind of brief overview of new stuff that is in our most recent release of the package. So some new features include the ability to calculate the amount of a solar eclipse as a function of time. So in other words, how occulted is the solar disk as viewed from a particular location as a function of time, which would be very useful, especially for the both the annular eclipse last at the end of last year, and then also the total solar eclipse next month. Two things that came out of the Dash meeting that came out as a result of the Dash meeting back in October, where I think a lot of us attended, was that the realization that a lot of people want to use spice kernels, but spice kernels are difficult to use. I'm really not going to speak much about what spice kernels are, but if you know about them, you know that they're often kind of difficult to wrangle. And so one of the recent additions to SymPy is the ability to interact with spice kernels via the AstroPy coordinates framework. And that's actually using a wrapper on top of the spicy package. And then another kind of result of these discussions at Dash was the people also want a lot of coordinate frames that are important, especially to people in the PyHC and broader heliophysics community. Are these coordinate frames that depend on the orientation of Earth's magnetic dipole. And so we also have 3 new coordinate frames exposed through SymPy that can be used again through this AstroPy coordinates framework. I'll show some code in a second. And we have a couple other kind of more minor additions. We have support for Gong synoptic magnetogram data, some new methods for determining visibility in helioprojective coordinates. So that's basically, if you have a coordinate somewhere on the sun, is it blocked by the solar disk? And then also some improved support for whisper data from Parker Solar Probe. So since our version 5.0 release early last year, we've had it's just kind of a summary of the kind of activity on the SymPy repository. But the one thing I wanted to point out is we've had 19 contributors to the last release, and 7 of those were new contributors. So these people that had never contributed to SymPy before and had their first contribution in the 5.1 release. So we're obviously, we still have kind of a somewhat steady stream of new people contributing to the package. And if you want the full kind of rundown of what's new in the 5.1 release, you can go and click on this link. We try to provide for every release like plain language summaries of like what went into the most recent release of the package. Okay, so so I'm just going to focus on the 3 of these new features here. So one of these, I think I mentioned, is the ability to calculate the amount of a solar eclipse. So how much is the disk occulted by the moon as viewed from somewhere on Earth? So all of this works using this AstroPy coordinates framework that the SymPy coordinates capability is built on top of, and I'll talk a little bit more about that in a second. But the basic idea is that I first can define a location on Earth using this class that's available through AstroPy, and so it just takes a latitude longitude pair, and then returns to me one of these sky coord objects that I can then do coordinate operations on. This is actually the longitude for Rochester, New York, here in the U.S., which is where I'm going to see a solar eclipse in April. I can then define an array of times that I know are kind of like roughly centered on when I think the eclipse is going to happen, and then I can pass this observer location as a function of time to this this new function we have called eclipse amounts. I'm importing this from our sunpy.coordinates.sun module. And then I'm passing in this time-dependent observer location, and you can see this is what I'm plotting here. So I'm plotting the amount eclipsed, if you will, as a function of time. You can see around about 3:20 in Rochester is where we're going to see about 3 minutes of totality. So again, this works for you could use any location on the Earth as defined by these sky coordinate objects, and then you can sort of use this eclipse amount to then predict, when the total solar eclipse will start, or when the partial eclipse starts, when the total eclipse starts. Okay. Next kind of big feature that was added in 5.1 was, like I said, this ability to use the SPICE kernels through the AstroPy coordinates framework within SunPy. So briefly, SPICE is this sort of system for defining spacecraft location and orientations. And the idea is that it's sort of a language for missions to express what their instrument and spacecraft orientations are. This now can be you can use this functionality through the AstroPy coordinates framework. So there's a bit of setup involved in actually downloading these. So these kernels are typically packaged as files, and so you need to download, particular, depending on what instrument you're using, you need to download the file. That's once you know that file, this is fairly easy. You just call this spice.initialize, and you pass it the files that you've downloaded. You can then use let's say I define, if I wanted to look at a trajectory of an instrument as a function of time, I can define an array of times, and then I can use this spice.getBody function to get the body that I'm interested in. In this case, I'm looking at solar orbiter. I'm passing in the array of times, and then I'm saying I want this to be in the what SPICE frame I want this to be in. This is the solar orbiter heliocentric Earth equatorial frame. And then I can print out, okay, so this is just, I'm just highlighting, basically what I just said, the bits that are relevant to this functionality. If I then print this, this resulting, this spacecraft that comes out of, or this object that comes out of the spice.getBody function, I can see that this is a sky coordinate object. So these are the same coordinate objects that we're used to working with in the rest of the AstroPy coordinate stack. And then here, I'm just plotting the radial distance from the center of the sun in AU as returned by this function in this particular frame. The advantage of kind of using this framework is that, again, I can easily transform between these frames. This is another frame that's defined by one of the SPICE kernels, and I can transform to this frame provided by the kernel by simply using the usual kind of transform to API provided by these AstroPy coordinate frames. And one of the other frames that's defined by Solar Orbiter is essentially it's the line of sight from the STIX instrument. So STIX is a hard X-ray instrument on Solar Orbiter. And in this frame, the 0 degrees is the anti-sun direction, 180 degrees is the sunward direction. So I can also, this is just making the point that I can use the same API to interact with all these different SPICE kernel frames, and again in the same way that I interact with the kind of usual AstroPy coordinates framework. One of the other useful things that you can get the field of view of these instruments, and again, this is defined in the frame of this particular instrument. But then if I wanted to work with this in terms of our usual helioprojective frames, there's a method called toHelioprojective, and then this returns me a sky coord, something that I can lay on top of, for example, a map as observed from a different observer location. And this is important for saying, is there overlap between these two instruments that are at very different observer locations, which is important for multi-instrument studies. All right. last kind of big feature added is these, like I mentioned, these new frames that depend on Earth's magnetic dipole. So I will say right off the bat, I am a solar physicist. I don't use these coordinate frames ever. I don't know that much about them, but I do understand that these are heavily used by people more on the magnetosphere side and people that are a part of this community. And these types of coordinate frames were kind of a big topic of discussion at the Dash meeting because they're difficult to define without this additional information relating to how the orientation of Earth's dipole at any given time. So these are the geomagnetic frame, solar magnetic frame, and this geocentric solar magnetospheric frame. So I'm just showing a code snippet that basically shows how you would set a coordinate up in using one of these. So you can import the frames, you define the frames using a particular observation time, and then you can build, again, these same sky cord objects using this is just like a Cartesian pair. These are fractions of an Earth radius or the scalars of an Earth radius, and I just define the frame using this frame attribute. Importantly, these, like I said, these depend on the Earth's magnetic dipole as defined by a particular IGRF model. And there are different models that you can choose using this magnetic model attribute, and you can choose different models when you instantiate a given frame. And it's just pointing out that when I change the frame, I can then access what model I'm using as an attribute on that frame. Okay, and then that's all great, but I think the most powerful, the point I want to make with this slide is, so this is a kind of a confusogram a bit. What this is showing is all the different, or several of the different frames that AstroPy, coordinate frames that AstroPy provides, and all of the circles shown in white are frames that are provided by SunPy. And so what SunPy is doing is it's augmenting this AstroPy coordinate transform graph by tacking on these additional frames. And so now that we've tacked on these geomagnetic, solar magnetic, and geocentric solar magnetospheric frames, that means we can get to any one of these other frames from those. So that's just kind of what I wanted to point out, is that this is the power of using this sort of approach, is that by implementing these frames in that way, you then have easy access to all the frames defined by AstroPy, and then all the other frames that are defined in the SunPy coordinates framework. Okay. All right, and then I will let Stuart handle these last two points. But so just let me know when you want me to change the slide. I think there's only 3.
Yeah. So one of the other things that we've been working on recently is a successor to PFSSPy. For those of you who don't know, David Stansby, who developed PFSSPy, has moved on out of solar physics. And archived PFSSPy and various other packages. SunPy Core has adopted a lot of the functionality that was, for instance, in HelioPy and various other things. But one of the things that as yet has not been continued is the development of PFSSPy. So in the last few months, we've spun up this new package that, after significant debate, we called Sunkit Magex. That which is now available under the SunPy org on GitHub, with all the functionality of PFSSPy in. We haven't done our first release of it yet, but we're not that far off now. PFSSPy has been used to do lots of very interesting science over the last 5 or so years that it's existed. So we're very keen to get a well-maintained successor to that package in development. We've also adopted the Stream Tracer package that uses compiled code to do field line tracing. So if you are using PFSSPy, you will need to transition to use Sunkit Magix, but we're trying to make that as easy as we can. But if you're using Stream Tracer, you'll need to do nothing because we've just adopted that under the same name. If anybody has any other extrapolation methods that they use in their work and would be interested in contributing to them. We are hoping to extend Sunkit magx out of being just potential field source surface into various other extrapolation algorithms as well in the future. Slide me. Finally, the other big area of work that's been going on recently is some tooling to automate a lot of the maintenance, boilerplate maintenance work with SunPy. SunPy now is up to like the SunPy core team, if you want to call it the SunPy project itself, maintains quite a number of packages at this point, as well as the core package. We have like packages like Sunkit magx and various other affiliated packages that we maintain, and keeping all of those packages having a similar development experience for contributors, and also keeping them all up to date with the ever shifting landscape of Python packaging, linting, testing, and all of the other things that go along is a lot of work that was mostly being done by Nabil when he probably should have been sleeping. So what we've been working on in the last few months is a way of automating a lot of this, or as much of it as we possibly can. So there's a few components to this. Firstly, we've brought up to date the Open Astronomy Packaging Guide, which is available at that URL. The Open Astronomy Packaging Guide is a concise and opinionated packaging guide that will get you a package that looks an awful lot like SunPy and AstroPy. And we've added various things to it and updated it to be almost purely PyProject based. But we've also added a GitHub workflow for a tool called Cruft, which allows you to automatically update your package with changes from a cookie cutter template. So for people who don't understand any of those words, cookie cutter is a Python project which lets you take a template and fill in a bunch of variables and have it as a directory on your computer. So if you run Cruft create Open Astronomy Packaging Guide that's there in that example, it'll ask you a bunch of questions like what's your package called, what's the description, who are you, where's your package, and then it will fill all of those variables in, add and delete files as necessary, and give you a folder which you can turn into a Git repo and start developing your package out of. What Cruft does is later allows you to run Cruft update, and it will try and apply all of the changes that have happened to the template since you initially rendered your project, and then that automatically happens every Monday on GitHub Actions for various SunPy packages now, including Sunkit magx. So hopefully we'll be able to keep all of those files synced and up to date. For anybody who is developing a SunPy specific package or wants their package to have a very similar development experience to all the SunPy packages, the SunPy package template has everything from the Open Astronomy package template, but with extra SunPy opinions, such as our exact linting rules and test workflows and that kind of stuff. Cruft is very cool. If you have ever used Cookie Cutter, I would recommend you using Cruft. When we put this work in the NASA Stoffel proposal, I was expecting to have to write Cruft, but I found it, so that was nice. Is that the last slide, Will? I think, yeah.
Yeah, so this is just in summary, and I think we're running short on time, so I'll just leave that up here and take questions if we have time.
We have time for like one quick question. It looks like Rebecca answering or asking questions in the chat. Does anyone else have a quick question for them?
This is Pete Riley. I did have a quick question about Stream Tracer. It looks like in the documentation, it's the actual tracing is done in Rust, but you have to install a Fortran compiler as well.
Stream Tracer 1. 2.x had the extensions written in Fortran. Streamtracer 2.x has them written in Rust. If you are building 2.x from source, you will not need a Fortran compiler. But there should be binary artifacts of both available on PyPI, so you shouldn't necessarily need any compiler. But
okay, great, thanks.
The Rust implementation is currently slower than the Fortran one, but we're working on it.
Oh, by how much?
Oh, I can't remember. A few times.
A few times. Okay.
It's not parallelized, whereas the Fortran implementation used OpenMP, but I have a working version of some parallelism, but I don't know Rust very well, so it needs a bit more work.
All right, thanks.
All righty. Thanks, Will and Stuart. Next up is Plasma Pi.
Cool. Are they showing up?
Yes.
Awesome.
Plasma
Okay,
Pi.
I hope everyone's enjoying the time change. It's like living a real life off by 1 hour, at least for those of us in the US. So I'm going to give an update on Plasma Pi. First, a quick introduction of the project, and then dive into some new functionality and a bunch of package infrastructure updates. So the mission of the Plasma Pi project is to grow an open source software ecosystem for plasma research and education. So it's very similar to PyHC, including not only heliospheric and astrophysical plasmas, but also like laboratory plasmas, magnetic fusion energy, high energy density physics plasmas, plasma chemistry, and things like that eventually. So it has we have a few particularly well-developed subpackages. Our particle subpackage is the one that's most generally usable and contains representations of ions, electrons, fundamental particles, compatible with AstroPi units. We have a formulary which includes the commonly needed formulae for calculating things like the Alfvén speed or those horrible Brudzinski transport coefficients, a bunch of things like that. We also have a dispersion subpackage, which contains dispersion relation solvers for plasma waves, including like two fluid, kinetic Alfvén, and now MHD waves also. We have an analysis subpackage that is designed to contain techniques for analysis. So some of the functionality is for analyzing laboratory diagnostics. And we also have a prototype magnetic null point finder. And we also have a diagnostic subpackage, which contains the more laboratory-focused functionality, including some for magnetized plasma experiments, and then also high energy density physics. To give a quick example of plasmapi.particles, which I mentioned is probably our most broadly applicable subpackage, we can create a proton object, give it the particle class a string, and then the proton has attributes like mass, and then methods like is category, so you can figure it out if a proton is a baryon or not. And also we have a particle list subpackage, class, which you can use to represent multiple particles at once. And then you can get things like the charge. So it's a fairly similar API to particle. All right. And so that was the quick update. And now I'll go into some new features and updated features. And the ones I'm going to talk about are all by students. So the first is refactoring our particle tracker. And this is done by Jaden Roberts at the University of Rochester. And doing that is motivated for some of the high energy density physics functionality. Then Tristan Simon, who's an undergraduate at University of Colorado Boulder, added a few classes for MHD wave dispersion relations. And so these include the Alfvén wave class, and then classes for both a slow magnetosonic wave and fast magnetosonic wave. And in turn, working with me, Mohammed Haq ended up adding a few classes for 1D ideal MHD equilibria. And these include both a Harris-sheet equilibrium, which is used for simulations of reconnection, as well as the famous Lundquist solution for flux ropes that are force-free. Then also, Elliot Johnson, a grad student at the University of Delaware, added functionality to calculate the thermalization ratio for plasma in transit due to Coulomb collision. So this is for plasma that is traveling in the, for example, the solar wind. So the applications, So the application primarily is for the solar wind, and you start out with like a particular temperature ratio for different ions, and then it thermalizes over time. And so it's able to predict the temperature ratios over time. And Elliot is going to be graduating fairly shortly and is looking for a job and has done very excellent work on Plasma Pi and then also for his own research. All right, so we also did a bunch of infrastructure improvements. And one thing which is mostly for the package developers is that we have been adding static type checking. So in particular, we've been expanding the use of type hint annotations. And if you haven't used those before, you can have a function and then you have a parameter to it. And then you can specify as an annotation that you're expecting an int to be passed to it. So number should be an int. And then the output is expected to be a string. And so these annotations by default don't do anything at runtime, but more serve as documentation and as a way to make sure that the types are consistent with each other and that like you're not trying to use an attribute that a certain type doesn't have. We, I think the beginning of this year, enabled MyPy as one of our GitHub Actions continuous integration checks. And what MyPy does is that it validates type hints and makes sure that we're using different variables correctly. And MyPy is really helpful because it can help us find bugs without running the code, and it can help us find problems with the annotations. So it is pretty useful, though it can be a bit difficult to understand the output of MyPy errors. We've made the most progress on particles and formulary, both of which already had reasonable type hints already there. But some of them, like we found a couple of times where the type hints were not quite right. And for package maintainers, if you're thinking about adding or enabling static type checking, I strongly recommend going to MyPy's documentation. They have pretty helpful advice on like how to enable static type checking on an existing code base. So it has suggestions like start small, have everyone use the same settings, and sorts of things like that. I also spent a lot of time, I think just the last month or so, working on speeding up continuous integration checks. And one of the things that we're doing is caching the .tox directory in GitHub Actions. Tox is the test runner, and what it does is create the Python environment that get used in the tests. And formerly it had been doing it in every time we ran a test, but now caching the .tox directory, which stores all of the stuff that Tox stores, it stores the Python environment between runs. And we use pin dependencies to make sure that it doesn't have to rebuild it too often. So yeah, so there's no need to rebuild the Python environment in every time we run a test, which ends up saving about a minute per run, which is a lot. We've also been pretty assertively decorating tests that take longer than a fraction of a second with pytest.mark.slow. And by doing this, we're able to skip slow tests with a particular pytest command. And this means that when we do a GitHub action, we can run 96% of our tests in 50 seconds. And previously, like when we're running our full test suite, it can take, it was like 2 or 3 minutes or so. So this is a pretty major speed up. But we just do still run the full test suite because we need it for code coverage and because how else would we find errors otherwise? Something that's new in the Pythoniverse is a package called UV, which is meant to be a replacement for pip, and it was created by Astral, so by the makers of Rough. And so it's pretty straightforward to implement. If you had pip install Rough, you can do UV pip install Rough instead, and it'll be able to solve the environment a lot faster. And UV is written primarily in Rust, which, as everyone who works on Rust will tell you, it leads to high performance. Except maybe not compared to Fortran if you don't parallelize it, as we learned from Stuart. All right, and I don't want to go through all of this, but I'm going to post in the meeting notes right after this a bunch of helpful pre-commit hooks, PyTest extensions, and Sphinx extensions that we've implemented in the last probably year or so that have been like really helpful for us. And some of them are pretty straightforward to implement. Sphinx copy button will add a copy button to code examples in the documentation. And it takes like about 2 lines in docs/comp.py to implement. And hover xref, which is a really cool name. If you hover over a link, it will have a pop-up tooltip sort of thing of the linked page. So there's a lot of good stuff here, and I'll save most of it for the notes. So we went to the APS Division of Plasma Physics meeting last 2 years in person, and we hosted booths. And because the people who organize booths apparently like us, we got high traffic areas, and that enabled us to talk with a whole bunch of students and early career scientists. My favorite feedback, which was from 2022, was, "I love your plasma dispersion function." I've never had anyone come up to me and say that before, so I really appreciated it. So it does show that there is a need in the plasma community for things like Plasma Pi. It also gave an in-person tutorial. And one thing I wanted to bring up here is maybe we should have a PyHC booth at heliophysics meetings. So I wanted to mention a few challenges also. Our most pressing one is that our current NSF award will conclude by next spring. I did an extrapolation, and it looks like next March is when it will conclude. And we don't have subsequent funding lined up yet. But we did apply for a successor NSF award, and we're looking for opportunities in DOE, though DOE, Department of Energy, is not as well organized as NASA or NSF for open source opportunities. So we shall see how that goes. There's also work to do improving the integration of Plasma Pi with other PyHC packages. And one of the most straightforward ways to do that is through using astropy.units, which can help make other PyHC packages more interoperable with plasmapi.particles and plasmapi.formulary. We also have some functionality to represent ionization states, so charge state distributions in plasmas. And there's potential for better overlap with several other PyHC packages. In the longer term, we could potentially have functionality in Plasma Pi for using plasma diagnostics, both in space and the laboratory. So being able to use the same software to analyze data from these very different environments. Another one is the plasma science data environment. Data sets in solar physics are at least somewhat well standardized. In plasma physics and fusion energy sciences, not so much. So that ends up being a pretty major challenge. And then also changing the culture across the plasma community. To that end, and as part of a different effort, helped organize a psychological safety workshop, and a couple of people from PyHC, who I think are on this call, attended that. And we're hoping to do that next year also. Then our last challenge is onboarding new contributors. And on that front, we're in the process of planning a summer school or workshop, which will act as a sequel to the virtual Plasma Hack Weeks that we had over the pandemic. And the idea is to cover not so much how to use Plasma Pi, but how to contribute to open source packages like Plasma Pi. And we haven't finalized the details yet, but it's likely to be at Bryn Mawr at the end of July, at the beginning of August in this month. And we're going to have like 3 days of tutorials, and then the last day, possibly an open hack session. As part of our NSF award, we can support travel by about 20 participants. But as I mentioned, we're still finalizing details, and so there's more to come soon. And so we're having a PyHC summer school this year, but maybe we could have a how to contribute to an open source package summer school next year, or have them sort of intermittently if we want even more summer schools to organize. So I think that is it. So thank you. All right, any questions? And I don't see the chat, so someone had to read it out loud.
Let's see. I had a super quick question. I think Rebecca also has one in the chat. You said it'll be July 29 to 32 at Bryn Mawr?
Yes, and by that I mean August 1st.
I figured. Where's Bryn Mawr?
Oh, it is outside of Philadelphia.
Oh, okay, thanks. I am not super familiar with East Coast things. Okay, Rebecca, you had a question in the chat.
And I see it now. There's an NSF call for setting up archives of NSF data, e.g. plasma science data. I should look into that. I don't know the details of opportunities like that. But yeah, that would be really helpful. Awesome. All right. I think we can move on then.
Yeah.
I'll post the things in the notes.
Thanks, Nick. All right, let's go right
And
on.
not a question, but just a comment. I love seeing static typing in Python code. So congrats for going that far.
Yes. All right, we've got a happy update.
Yes. Okay. Can you hear me?
Yep.
And let me switch this to the slideshow. How's that? Okay. Thanks, everybody. Here to update you on the Happy project and effort. So focusing on adoption updates and some new features. So I'll give a very short overview of Happy. Most people probably know what it is, but in case you don't, there will be a few slides on that. And then focusing this time on, because Happy is a spec, focusing on the adoption and usage, what organizations are using it and what servers are available and tools, and a few highlights from our version 3.2 and then what's next. So if you don't know what Happy is, can mean several things. At the fundamental layer, Happy is a specification, so it's a standard interface shown here where you have a client making a request with a defined request structure that's very simple. Data set and time range is all you really have to specify, and then you get back a stream of data in a certain defined transport structure, transport format. So give me the data and you get back a stream of ASCII or JSON or binary. So it's a specification. People sometimes talk about Happy, they're talking about Happy servers. There are servers that implement this structure and offer data. And then there's also clients that know how to set that request up and receive the response, both client libraries and full analysis tools that sort of have Happy hidden inside them. And of course, the Happy Python client, that's the reason why we're here with the PyHC, is that we do have Python capabilities with Happy. So again, Happy it's providing easy access to time series data. If you have data that are in some kind of tabular format, indexed by time, and you have different columns, that's what Happy is designed to serve. And it was designed around specific science domains listed here. Mostly it started with space-based, like in situ particles and fields, but also ground-based magnetometers was a big part of the initial push. But any kind of time series data, ephemeris, there's various solar indices or space weather indices. And other areas that we're pushing into, ground-based ionospheric data like Madrigal, I'll say more about that later, and NOAA space weather data, SWPC, the Space Weather Prediction Center, model outputs. There's a lot of Earth science data this could be applicable to. It's the heliophysics application programmers interface, but it doesn't really have any heliophysics specific stuff in the API, so it is applicable for the things too. All right, so this is just the cartoon representation of why a standard interface is good, because if you have multiple different services, they all have developed their own highly functional and useful APIs. And so communities develop tools and end up using those APIs, which is great. But then if you want to start working with data from different places, you end up having to read the documentation for each of the specific ones. And you could do that, but it ends up being a lot of different types of data access code that you need to write. So Happy is designed to be a common interface, not to replace what's there already, just to supplement it. Here's a low-level, very basic way to just get to the numbers. And so the data wrangling code that you write for one works for all of them. So that's Happy in a nutshell. The spec itself, I'll say, is now at version 3.2. Literally right after this meeting, we are having the Happy developers meeting where we push the merge merge on the pull request that will make 3.2 official. So we're a little bit slower on that one than we wanted to because of some of the things we were adding in there were tricky. We wanted to make sure we got it right. And I'll talk about that in a minute. But here's the timeline of the versions over the last few years. But 3.2 is literally coming out today. So that asterisk will disappear when I submit these slides to Julie for inclusion on the meeting website. So historically, Happy was developed by people at multiple different institutions. Bob Weigel at George Mason, he kind of had the first time series data server up and going, and then I also had one for some Cassini data. And Jeremy Faden's been involved from the beginning as well. A lot of folks from Goddard. And LASP was involved, UCLA, Todd King. They have some planetary data there, but it's the same type of magnetospheric fields and particles data. So these are the institutions that got it started, but it has branched out beyond this. And this is where I'm starting to talk more about adoption. So there's the AMDA server at IRAP in France. The ESA folks are starting to use it now. The Swarm mission, their data, they have a Vires computing system. And so they have a Happy server and some Happy clients for analyzing stuff there. Intermagnet is ground-based magnetometer chain that offers Happy data. And then the Royal Dutch Meteorological Institute, acronym is KNMI. They have a Happy server and a really nice client. I'll show that in a little bit. And the HelioViewer project offers Happy server as well. So these institutions are not really associated with the development team, but are using it now to offer their data in this standard way. This is interesting too, because we have some new projects that are coming online. The NOAA Space Weather Prediction Center has become interested in it, and they're going to be pursuing it for maybe one of their current servers now, and for an upcoming mission, they wanted to offer a Happy capability. So they're meeting with us, talking about which server capabilities they want to use. Space Environment Canada is a project that's ramping up, and they've expressed an interest in Happy. And eventually we are pursuing and have been in talks with the Madrigal folks, and they're interested as well. So this is part of the update. It's like, yeah, this really is catching on. I feel like we're kind of at the knee where we're going to see a ramp up in adoption. So how can Happy help you? In other words, what data is out there? That's the most common thing. Well, can I get to my data this way? So this is a list of the established servers. I'm not going to read this in detail here. I'm going to show a different slide that has this because these are accessible through kind of a convenience page that we maintain. So that's this page right here. This is a list of the known production servers, and you can go there and select one and start exploring data online using this web page. This is not really meant as the primary way to interact with Happy, but it is a super useful way to get started, because one of the things you can do here is, in addition to either downloading data or getting plots, you can ask it to write the script for you. How would I get this data in Python? And it shows you that, or IDL, or MATLAB, etc. This is a great way to sort of see what happy data is available, and we routinely update the list of production servers when we find out about new ones. And if you click this this QR code on your phone, this goes through this site here and generates a specific plot that you can, it's running it all the way through, and it'll just show you the data. Again, that's not really publication quality plot. It's more just like, is there data there for this thing that I'm looking for? Right. All right, so a lot of these different servers that have come online, what have they used? What technology, or what Java or what happy server are they using? So there's one at SSC Web that's using a Node.js server. We kind of consider that a pass-through server, where it's not necessarily running at the site, but it contacts the site underneath and provides a happy interface on top of it. That Node.js server is super useful because it handles all the happy stuff for you, and then underneath you write a script that goes and accesses your data, and that can be in any language that you want. C2Web is up and running. It has an older Java server that's in use right now. We're going to be updating that one soon. And then this whole list of other servers, they just implemented Happy and just added it into their existing server capability on their own with little contact from us. So that was very encouraging. That meant we did a good job writing the spec. And so that process is meant to work that way. Read the spec, and then you can implement the server. And then the Cluster Science Archive at ESAC, they're using the newer Java server that we're actively working on. And there's a few bullets here about that. Other places that are using that one. NOAA's looking to use that one as well, the Space Weather Prediction Center. And we'll be updating C2Web to use the next generation Java Happy server. And there's at ESAC as well, in addition to the Cluster Science Archive, there's other archives there. And they have a more sort of generic approach to some of these other missions beyond cluster. And they're working on incorporating Happy Server into that mechanism as well, after which many missions at ESAC would be available through Happy. So what about a Python server? We do have one. It's been used some, but it's not been in production use for a while. So that's one we're still looking to improve. We have applied for some NSF funding to put this through as kind of a cyber infrastructure thing for NSF. And if we get that, this Python server would get a big boost. Okay, so that's on the server side, what's available. Now on the client side, if you want to go analyze Happy data, the intent here really, Happy is just a transport mechanism. Go get me the data, bring it into my application. So you'll not want to do that yourself. You want to use some client code for that. And so there are some popular tools that have already got that client access built in, and it sort of hides it away from you. And so there's a list of the tools there. Some of them are open source. There are some other explorations of Happy that are going on as well. Brent Smith is looking into some model access using Happy. Sandy in Tunis has an HTM grant looking at accessing local data to merge that with data that you're getting online and do a kind of an amalgamation of data from different Happy servers. That's going to be really interesting and useful, as will the model access as well. So, okay, 3.2, like I said, is coming out. I don't want to necessarily read through this whole list, so I'll highlight a few things, but it is backwards compatible with 3.1. A lot of the things that we've added are optional things that a server can now do. We really carefully consider any required things because that breaks existing servers. So we haven't broken anything. If you implement 3.2, then 3.1 clients will still be able to read from it. We do have a full changelog for this, and I've sort of pasted in a modified version here. So I'll just highlight this one here, the catalog. In the past, the catalog would just list out the names of the data sets, and you had to hit each data set with a separate request, an info request, to find the metadata. Now you can ask the catalog to go deep and just show you metadata all at once for everything. A lot of people were asking for that. And that's an optional feature, and the server can advertise whether it's capable of doing that or not. The other thing I want to emphasize is this one. This is partly what took us so long to get 3.2 out. And a lot of requests for, well, how do I serve images using Happy? And that one, I won't go into all the details. We just didn't want people listing out their data files and saying, oh, I'm listing my data through a Happy server, when all you were really serving was a list of files. But for images, that's actually okay because people know how to read in and interpret image data. Whereas, other types of files, CDF or HDF or whatever, you really want Happy to expose the content, not just the list of the files. So, but for images, you can list URIs that point to the image files. And so now there's a way that you can indicate that you're doing that using Happy 3.2. A lot of people were doing it already, just not quite in the same way. So we just wanted to emphasize the standard way to do that. So about that a little more. So here you would just list one of the columns in your file is now a URI string that should be some actionable way to get to data. We say URI rather than URL because it could be like an Amazon S3 bucket, or it could be, some other protocol for getting to the data. But it needs to be actionable by the, clients would have some general expectation of being able to get to it. Here's an example of the timeline viewer, an open source JavaScript front end that can show you data from Happy servers, and it's showing images as you scroll along. These images will change according to what time point you're looking at. So that's very cool. And this tool is what got the NOAA Space Weather Prediction Center interested in Happy. They're like, oh, we could just use that tool, which means we need to put a Happy server up. So we're starting to get the chicken and egg problem going here where, oh, there's enough client capabilities that people are interested in now supporting it on the server side. So next steps, one of the things that I'll back up for a second, this timeline viewer here, if you zoom way out and now you're looking at a year's worth of data, you probably don't want to be pulling the 1 second data to make your 1 year plot. So this server knows that as people zoom out, it should switch to a higher cadence or a higher interval, lower cadence data set. And we want to make that an official thing in the spec to be able to link data sets. Hey, here's a list of data sets, each with different cadences, but they've got the same stuff in there. We've had people ask us about provenance. When I get a stream of Happy data, give me the list of DOIs of content that went into that. So we're going to think about that. Right now we have a list of all the known Happy servers. We're sort of maintaining that ourselves. We're going to look at ways we could come up with that list more dynamically. And we do have some JSON schema development that we've been doing that you can check all the catalog and info responses and so forth. But that's done, but we'll have it a little cleaned up for the next version. And I mentioned some of these other things that are ongoing already. We did put in for a large NSF effort to bring Happy to multiple NSF data centers, and we'll see how that goes, probably hearing back this summer. So I think that's it for now. I'll back up to this one here if anybody wants to pull up the fun plot. There's a bunch of stuff in the chat. I'll pull that up. Or if anybody wants to just jump in, please do.
Oh, go ahead.
I have the hand. Yes, I hope it will be a quick question. So, sure. John, I think I asked this before, but can you tell what's the major difference between Happy and the DOS2 servers?
Yes, DOS2 servers have a very similar approach, and Jeremy Faden, who created that, was of course on the panel from the beginning, helping us with Happy. DOS2 is more complicated and has more features. So you can do a little bit more with it, but it's also a little bit harder to implement. It has capabilities in there where, for example, if a data set changes midstream, like, oh, we went from having 25 energies down to just 10 energies, the DOS2 stream can communicate that midstream. Yeah, DOS2, it's DAS2 is the name of it, data analysis something. It's the interface that Jeremy created for talking between servers and clients. It's a more complicated version of Happy. Mm-hmm. That's the summary.
Thank you. Mm-hmm.
Okay.
Not DOS, like Windows. So,
Yeah, it's das2.org, I think, the website.
yeah.
Awesome. Thanks, John. If there are more questions for John, put them in chat. We are going to go ahead and move on to the next one, which is SpacePy.
Two Johns in a row. I apologize for my office side of giving you the side of my face here.
Adds to the intrigue.
Yeah, intrigue, that's the word for it. Okay, so just a quick update on what's happened with SpacePy since our last meeting last May. So we talked about being for space science data analysis and modeling. Most of the domains that we operate in as developers are magnetosphere and heliosphere. So big news is the 0.5.0 release went up on PyPy about 3 hours ago because I really wanted to have a release for this talk. So what's in that? The big thing is a whole bunch more binaries. So got binary wheels on all 4 platforms now. I'm saying 4 because Macs really are 2 platforms these days. And that also includes the NASA CDF library. So in theory, you should not have to, regardless of platform, think about a compiler if you're on any reasonably current system. And you don't have to go looking for the NASA library either. Part of that was the migration off of distutils to setup tools and getting away from the explicit NumPy distutils. The annoying thing that they didn't say when they were getting rid of NumPy distutils is that F2Py's interface is completely changing. And it's requiring Meson. So this is not quite done in the sense that for our own purposes, next release, we're going to kill F2Py and just use C types. But none of this should be end user visible unless you're having to build from source for whatever reason. Although on that note, if you happen to want to be playing around with stuff, we now support edible installs. And we have stuck a knife in the back of Python 2, requiring 3.6 at this point. So what else is in here? I had mentioned this as a coming soon back in May. Soon has been longer than I wanted, but we are now actually parsing ISTP metadata within space data objects in CDFs. If it happens to be there, it's not a requirement, but if it's there, you can literally just open up a CDF, grab a variable and say plot this. And that will be the basis of some other stuff we're working on. A couple of little things on PyBats from Dan. We can do parallel perpendicular velocity calculations, just extracted out of the simulation. A little bit more flexibility in your quick plots. If you're really into the details of how quad trees get built, you can specify a little more. And similarly, at the request of Komodo, we're not sorting the unstructured binary inputs. So that structure is kind of being maintained after the read. Other new feature is Urbim has this dose. Wow, it would be nice if I could spell. It's a dose calculation model, not a dose calculation model. We're not calculating number of deer. So this is now exposed through UrbimPy. So if you're interested in exactly what radiation dose a human's going to get behind a certain amount of shielding, hey, we've got that support now. Just the numbers on here since May. Just over 100 commits with 4 contributors, 24 new issues, 9 closed. Again, the installer has been such a huge focus of the time. A lot of other stuff hasn't been done, but it also means we have several installer-related issues that I'm going to go through and just close as, hey, try the new release. So that helps. Mostly keeping up with the PRs at this point. And we're starting to move into GitHub discussions for kind of first-line design and support. So that's why the issue count is starting to go down. And hey, 1 release as today. Hopefully, we're going to be a little faster on releases going forward since I've done a fair bit of automation support as well as the installer updates. So what's coming up? Whether it's 0.6 or 1.0, not sure, but we are desperately trying to shoot for something we can call a 1.0. It's a little embarrassing to be at an 0 point at 14 years in. So we have a little bit of NASA support still running down that we got about a year and a half ago, mostly in terms of trying to be more responsive to issues. If you remember from last time, our designated developer for this left the university as soon as we got the money. So this point, I have a couple of undergrads lined up that we got a no-cost extension. So I should have a couple undergrads working on that through the spring, but then also hitting things quite hard during the summer. So, and they've come up to speed pretty good on some other projects. So they should be able to hit the ground running on this. Showed this before, this ability to adopt between PyHC data objects. We've got a bunch of really open pull requests that just need to be tweaked. Haven't forgotten about this, and this will be pretty awesome when it lands. And John Vandegrift was really behind this, and again, the installer kind of pushed this back. We're starting to design out cloud file support and really not just throwing S3 at it, but saying what other things do people have that they kind of like to treat as if they're files where we are able to open a file. So open file objects, S3 of course, but also, hey, if you throw a HTTP URI into that, maybe that makes sense to open it. Byte streams you download, that kind of thing. Dan's working on some 3D SWMF support. This is being both hung up and facilitated by some discussions about some future motion SWMF, which will also be cloud related and such. So Dan's mostly driving that. Unfortunately, it's subject to Dan's time, but also means we're going to be kind of thinking about how PyBats and SWMF move forward in conjunction. So that should be pretty cool once it lands. What else we got going on? The other big thing that kind of got delayed was to really overhaul that documentation. It still, unfortunately, does look a little bit cranky. But based on deep processing, we've got a good idea of how we can have full auto docs nicely integrated with NumPy docs. So that should be coming up pretty quick. And whatever we're working on, you can generally see in the GitHub projects. So, and again, let's see if I can pull the chat. There we go. Cool. And so I'm open for questions if anybody has them. Otherwise, I can yield my time and we can move on.
I have a question.
Go for it. I'm still only
Awesome.
seeing like 4 people at a time.
Awesome to see that you're building binaries. Are you now building those on GitHub Actions automatically with CI build wheel, or?
No, they're not on CI. When I was looking at CI build wheels, it was not looking like it was quite getting what we wanted in terms of stuff like on the Macs, we've got to be able to do the build against the specific SDK to make Conda happy. There also aren't Mac ARM runners on GitHub right now.
There are, as of the last 3-4 weeks.
Yay!
You could CI build wheel would still build Mac ARM under virtualization, even though you couldn't test it.
Okay.
It
Yeah.
always...
No, it was really about getting the processes working in the first place, and then trying to move. So yeah, definitely interested in CI build wheels. Definitely interested in automating this more, but I was not going to hold up the release for the sake of
that's fair.
automation.
I'm pretty sure you can pretty much do arbitrary pre-build stuff with CI build wheel.
Yeah.
Well, yeah, I know it's complicated, but I was interested. The other thing, seeing about your S3 comment, is have you encountered the FS spec package?
Yeah, I think we looked at it, and it's definitely on the radar because this came up at the conversation that we had at the meeting last spring. And yeah, it's a pretty similar approach. It's just a matter of getting our head really around the use case and making sure this is the right way to go.
Yeah.
Cool. Anything else?
Maybe just to clarify here, so also join in people saying congrats on the new release. That's awesome. I was gonna be I'll be mentioning this as part of my PyHC environment talk tomorrow, but now I'm guessing it's going to be outdated because I've got 0.4.1 in that environment. But I am used to jumping through the hoops to install SpacePy of making sure that I have the CDF lib already on the machine, making sure I've got a right NumPy version installed first, and then I can do a pip install SpacePy with that no build isolation flag. And are you saying with all these changes, basically all of that's like gone now? You can expect it to just be a simple pip
As long as
install?
you've got a reasonable binary, it all goes away. So as long as you're running on something where there's a build. Now, if you're running against, when 3.13 comes out, until we get a new wheel, then that'll go away. But yeah, you should be able to just do straight pip install SpacePy. Don't do anything else.
Well,
I
that's
just
pretty
did it.
exciting, man.
I just did it on Windows, Sean. It works.
Woohoo!
The other thing, honestly, about ditching FTPI as well, I'm really desperately hoping this is going to do what I think it will. But once we ditch FTPI, the way we're doing our compiled code doesn't depend on the Python version either. So if I can finagle things right, which is a big if, we may be able to have binary wheels that are not Python version dependent. So
Very exciting time for SpacePy.
yeah. Cool beans.
Right. Thanks, John. Let's see. Next up is Komodo.
All right, let's see, go full screen. That look good?
Yep, thanks.
All right. All right, so I'm gonna go through the new features we got in Komodo, some recent updates. So it's just the recent stuff. I'm not gonna tell you what Komodo is, you should already know. So I'm just gonna go through some of the things we've done with more model readers in Komodo, some updates and new model driving using Komodo. So that's a neat new science application. Kind of a new happy interface. John mentioned that, and I'll explain on that a little bit more. This is a different way of using happy for some model stuff. And then some new web interface to visualization that we've worked on, some online easy front end for things. So model readers, currently Komodo has this list of models that are available to be used. The Gamera global magnetosphere model was just recently released. It uses custom C code as for its interpolator, just like SWMF. So this is a very complicated model, and so it has its own custom tools to do that. And so that was just recently released. Verb model reader is also under development. Sasha's here on the call working on that. We're very excited about that going forward, because that kind of breaks us out into another different type of unique model for Komodo to read that we can then use going forward to clone for other similar type models going forward. So some new model reader types going on, and some expansions going on there. The model driving in Komodo. So this is something that Josh Pettit has been working on. So ITM models are often driven by conditions at their upper or lower boundary conditions. And just ITM's ionosphere, thermosphere, metasphere. If you don't know what that ITM means, throwing on the jargon. But the models are often driven by some type of empirical driver or solution. But we can also recreate those drivers by processing output from other models. And so we can run model A. We use Komodo to ingest that model output, extract the data at the location, cadence, positions, grid, everything you wanted, all those conditions, unit conversions, all those things. Then we do the unit conversions, the coordinate transformations will then create a file that then drives model B. And so this allows us to do new drivers where Komodo is kind of providing the glue between the two models. And so what Josh has working right now is using SWMF now to drive GITM, WACMX, and TyGCM. Those are working now. He's close to getting AmGeo to drive those same models. Next on his list is getting a Delphi to drive that, and then adding CTIP is another model that we can drive, and then eventually doing other magnetosphere models as well going forward. So this is a new way of tying models together and providing some different flexibility and analysis, and be able to do more validation of model runs to see how they change with different driving and more dynamic driving. Because often those empirical models are just averaged over time, and they could be driven by something that's time dependent, can improve the physics there. John mentioned a little bit that there's new happy work going on with Brent Smith. That's something that the CCMC is funding a way to do fly-throughs of model output. And so the interface will allow a selection of a model run at the CCMC, and then the satellite, and fly through, and then get back that time series data that Happy is typically serving. So it's using Komodo on the back end to read those options that are passed to it, do that extraction, and then provide that time series data. So I kind of think of it as a Happy interface with a twist, because in a normal Happy query, you specify an ID, for example, ACE, and then you ask for what variables and time and whatnot. And here you're going to specify three things. You got to specify the model, which run of that model, and which satellite. And so those kind of will then get combined into a new ID. So we're developing a kind of a new custom interface to make those selections easy, from pull downs and drop down menus and things going forward. We're getting close on this, and unfortunately it's not available to show you results here, but hopefully in the next month or two we'll have this online and available for the public to access these fly-throughs with this Happy server. One of the other big new things we've done with Komodo over the past 6 months, we now have 7 of the supported models in Komodo are available through a web interface. And so it's basically hiding some of the Python behind the scenes, but allowing people to use Komodo to look at model results and do visualizations. And so for those models that we've selected, all of those CCMC runner requests for those runs can be visualized. And so there's literally thousands of runs at the CCMC for those models that we can then peruse through and do analysis with them. And so the system is designed to automatically adapt to what variables are in the models, which may have different dimensionality. I'll show that a little bit in a minute. And then you can get 1D, 2D, and 3D outputs available. And then one of the unique things we added to this is each page then includes a link to the Python code that did create that plot. So if you have access to that same model output, if you've gone to our CCMC's page and downloaded that model to your own machine, and you go through our web interface to generate a plot, you can download the Python code that did that, and then you can do that and further customize to your heart's content and go forward with that. And I'll show you a couple of examples of that. So on the web page, there's a pull down for what model you want to be looking for. And the CTIP model, for example, has over 700 runs available at the CCMC. You can do some very simple searching by a string in this run name, or a date time period or whatever. And this page will allow you to view those model outputs in kind of the default CCMC visualization, but now we have an option to be able to look at that plot in Komodo and see what you can do with those results on the web. And so this is a simple example looking at a run of CTIP. When you normally first hit this page, this plot is not yet visible. And so you'll choose a variable, and that variable will show you, it'll give you the long name description, its units, its coordinate system. And Komodo will look at that model output and say, oh, this particular variable, is available in 4 dimensions. And so this variable density is a function of time, lon, lat, and height. And so if you set 3 of these, like I've done here, I've set the time, the lat, and the height. Then you set those 3, then it's a 1D plot result of the function of the unset variable. So this is a over the range of longitudes. Here's the density plot for that. If I would just set 2 of them, I'll get a 2D contour plot, for example. And so some of these options. And then down here at the bottom, you see this view Python script used to make this plot. So this plot you see right here, if you go and grab your own data and look at this little Python script here, and it says, hey, here's the path to the data. And there's the path to where you want to write your result plot to. And then go through a few of these steps. And it's broken up into a pretty fine grain where I set a bunch of variables. These could have all been rolled into these commands, and it could have been a long jumbled argument that would be kind of messy to see. But if you download this and want to tweak just one thing, and you could then go through and set a couple of things, options here. But then this will go through and it will actually extract or load the data into the reader. It'll extract that particular plot. It'll add a few customizations that I've done to make the plot a little more appealing, like laying on what the coordinate systems is and some of those label descriptions. And then it saves the output to an HTML file, which is then something you could load or embed somewhere else or fully interact with. If you don't want to do it in here, if you actually are doing this in the Jupyter notebook, this figure object is then an fully interactable object in the Jupyter notebook you can interact with. And so all that then allow you to use Komodo to do some visualizations without having to be an expert or have your own environment there. So this is just a sample of some of the types of plots that are available with this new online service. And so again, you can make these 1D plots, 2D plots here, choosing to overlay, shoreline boundaries on things. And you can see each of these plots are for a different model result. They're either in GDZ coordinates here. There's some of them that's just geographic coordinates. This is a SM coordinates. You can see here, this is the SM on the magnetic pole. Here's the little line right here that's shown on here as well. So you get a feel for how those fit together. And so all of these plot options are available. All of them can be redone yourself offline. So I'm going to try and do just a couple of these things interactive just to see how this goes and see if this works well live. Can you guys see the web page on top of the PowerPoint?
Sure can.
Okay. So this is now live on the web page. I'm coming in here, and you can see I'm looking at this plot. Again, when I'm here, it's very interactive on the web page. I can go and change that to a 3D plot, and it'll then regenerate. It's loading in the data. So there's the same plot in 3 dimensions, fully interactive in the page. And you can see if I go down this long list of variables here, and if I select TEC instead, you can see that TEC is now at the total electron content, and it's now a function of 3 variables, not 4, because it's a highly integrated value. So there's no longer a plot here that I can look at, and so that I can go and then generate that plot and reset the values. And so I can go and jump through, and here's all the runs for CTIP-E. I can go and look at all these other runs. TIEGCM has almost 2,000 runs available here, and so all of these have the option then of looking at them in the two ways. One of the ways to get to that, if you actually go to the CCMC's webpage and look at a default visualization, there's now a new link here at the bottom. So normally I would go and look at it with what's its IDL tools and visualize here. There's now a new link that says, hey, view this output in Komodo, and that will jump directly to this page. So it can all be discovered through standard output for those results. So anyway, that's the new web stuff. And then I want to show one last new thing here. And that's just some new visualization that we're developing that's using Komodo, that's not yet available on the web, but will be available soon, either on the web or in the ISWA toolkit. And this is SWF output. interpolated into Komodo. And so I know, John mentioned that Dan is working on some 3D things. We're working on 3D things with SWMF as well. But we're using Komodo not to just extract these slices, but we're also using Komodo to interpolate and find isosurfaces of relevance. And so this red translucent here is the bow shock at the front of that simulation. And so you can find that solution, and I can look at that, but I can also then turn it off. And then this next surface here is the magnetopause boundary, which we then calculated from various variables that the code outputs, and then extract it into a surface that we can then view. And so I can overlay that on top of a plot. We've got some field lines. Again, right now these field lines are computed with a different program. Eventually we're gonna be out doing tracing and calculations. And with Komodo, that's a future feature we're working on. If you zoom in here, you see that I've got, this is actually the Themis satellite position on the south side here. Here is MMS, and the MMS is cutting right through the bow shock and its calculation. Those are using Happy to grab the positions and overlay them into this one conglomerate view. So we're working on new visualizations that utilize Komodo, but try to provide new tools for scientists as they try to do these things. And so it's both using Komodo, but it's also putting some of it behind a front end, a web page that can allow more people to use it without being experts, but then also providing the source for people. And so we have a few beta testers who are taking these toolkits and these new scripts and Jupyter notebooks, and then adapting them to their own use as they go forward. So that's the end of my updates. I'll take any questions you have.
You just had a couple comments in the chat from John and then Jeremy.
All right, I just gotta find where I exit my slideshow here.
No worries. John had said it would be good to talk to you about the Happy mechanism.
Yeah, I can just jump in. Yeah, we'll chat sometime, Darren, because it'd be interesting to see. We've thought about, you have some complicated thing that you want to generate, and what ends up is maybe a temporary Happy endpoint that gets set up. Hey, your data resulted in this data set, and boom, here's the Happy server or set of endpoints to access that. That's kind of neat. I'd like to see how you've done that.
Yeah, that's we definitely want to loop you in. I'm hoping that Brent has been communicating with you guys a little bit as he's making tweaks and customizations to how the Happy will work with our need, but definitely want to discuss that further with you.
Thanks.
Darren, can I ask a quick question?
Yeah.
We have, as you know, the MAS and the COHEL runs that are at the CCMC with the runs on demand. And we also have our own SciPy routine for visualizing the data. But it'd be great to be able to use Komodo as a way for people to pull those runs on demand results. So I guess the first question is how straightforward would it be to get a reader for the MAS output into Komodo? I know I guess you've looked into that, or the team has looked into that before. Is that
right? It's not something that's on our next to-do list, but it really comes down to what your data structure is and how much unique features you need to be able to read and interpolate. If your data output is in a straightforward data structure, it's going to be much easier to go forward. So the ones that are being complicated, so SWMF, Gamera, Verb, those have something unique about them that is making them challenging to develop and has taken longer. But other models, if your model has things that are a little bit simpler, it should not be a challenging task to make a reader for that and add those tools. So I'd be happy to talk to you further about that and go through that.
Okay, great, thanks. And then a related question is that we have our own reader, and you're developing readers. And then Stuart was talking about his stream tracer. We have our own field line tracer. There's a lot of, I guess, efforts that are doing very similar things. And I wonder whether or not there's a way for us to leverage some of that more effectively.
Yes, I would love for that to be. I mean, I've looked. There's not good, hey, here's a free tracer that works with all these data structures, right? And there's just, I haven't found a tool out there yet, and so everyone's kind of developing it themselves. And so,
Yeah.
Lutz has an old tool he wrote in C, 15
Right.
years ago that we're thinking of modifying to work here. But certainly if there's some, shared, usage to get a better tracing algorithm that more packages can use, we would definitely be interested in that.
Okay, thanks.
All right. Thanks, Darren. We should go ahead and get moving on to the next one. And I believe it's PySpeedas.
Yes, good morning. Let me share my screen here. Can you hear me?
Yep.
Okay. And let's see. I'm getting full screen. So hopefully you can see that. So thanks everybody. I'm Jim Lewis. Let's see. There we go. Presenting on behalf of the PySpeedas core developers, which I've listed here. And we're also starting to get a steady stream of contributions from various anonymous benefactors. So that's kind of exciting. So I'm going to talk a little bit about what's going on recently and in the near future with PySpeedas. And one of the big things we're working on right now is improving our onboarding experience, making it more accessible to new users. And a big part of that is a documentation scrub. We've got pretty much all hands on deck, updating our doc strings, bringing things up to date, making sure they haven't gotten out of sync with the actual parameters. And then some things that were previously missing and kind of hard to track down, like for the given missions that are directly supported, sometimes it's kind of difficult to figure out like what are the names of the instruments or the names of the data sets or the levels or the cadences. And now we're trying to make sure those are all explicitly spelled out in the doc strings, so you don't have to go reading code or even worse, looking through the server indexes to figure out what's there. And we're also adding some type hints gradually. We've also been renaming a few things to make them a little closer to IDL SpeedS. So PySpeedas is a Python port of our existing IDL system that's been out in the community for quite a while. And we want to make it as friendly as possible for those users to transition over. So we're trying to make things consistent between those two systems. And then that has a happy side effect that if you make things easier for human readers, you also make things easier for AI systems. And we expect to see some benefits in like using AI tools to help us port more of the IDL code to Python. We've also added a number of Jupyter notebooks for new and existing features. And we recently went through and updated our notebooks so that they'll work in the Google Colab environment. So that means usually means adding a few magic commands to make sure the environment's set up, that PySpeedas is installed and has all the dependencies. And so now you can get to them from Google Colab. I think there's a GitHub option when you go to the root URL, and so it's fairly easy to navigate to our various repositories of Jupyter notebooks. Then by user request, we've also added a libs tool. This is something that exists in IDL SpeedAS, and it lets you give like a fragment of a name or a wildcard expression and look up routines that match it. So, for instance, if you want to do something with wavelets and you're not sure, like, oh, is it wave underscore something or was it spelled out? This gives you a quick way to find out what tools might be relevant. And then we're still a little more of an in progress task. We have the speedas.org domain, and we have a documentation wiki on there, speedas.org/wiki, and we're developing some new user installation and setup guides. So for somebody who's maybe brand new to Python, we lead them through the steps of what they need to do to get a working Python installation and set up a virtual environment and maybe even an IDE and basically everything they need to know to be able to use PySpeedAS. And so the reason we're making this big push now is we would like to have as many of these things in place as possible because PyHC Summer School is coming up. We do expect to have an influx of new users, and we just want to give them every possible opportunity to get up to speed and be successful. So just show you a couple of examples here of what our documentation's looking like now. This is a screenshot from our pyspeedas.readthedocs.io, and we consider this our main documentation repository. So this one happens to be an ERG, Arase load routine for one of the instruments. And so you can see here on the data type and the level parameters, we've expanded those out to let people know what the valid options are. And throughout, we're trying to explicitly call out any default settings to make that a little easier to navigate. And another thing, we've been trying to make sure that all our doc strings have examples embedded in them. Basically what's the simplest call you can make to do something useful with that routine. So, and we've reproduced those in most of our read the docs pages. So here's a sample using that load routine and plotting. This one happens to be spectrogram data. Some other things we've been working on. We're improving our plotting. So we've had various reports here and there. There have been some issues with, especially with spec plots, and these seem to be cases where a lot of times the y-axis binning will change over time as instruments go into different modes and different energy ranges and so forth. We needed to make sure that we've handled those cases correctly and make sure that the bin boundaries are reasonable at these points where you change over from one set of bins to another. And then we've also made some significant performance improvements in the process of getting things to plot correctly. Some of the algorithms we were using were quite slow, and we've managed to speed that up quite a bit. So we're pretty happy with that. And then we are working on some more options for line plots, especially with symbol shapes and colors. We have the in IDL SpeedAS and PySpeedAS, we have this issue or this concept of a pseudo variable. If you want to plot several quantities on a single plot panel, you can make a pseudo variable that's basically just pointing at like this, that, the other sort of base t-plot variables, and then have them all appear on the same plot. And that could be a little tricky to combine like the individual options on each of those variables and make a coherent plot. So we're working on improving that. We've been paying some attention to magnetic field modeling and tracing, and this is using the GeoPack PyHC package. So we were doing some IDL versus Python validation, and we did find a few problems with some of the implementations in GeoPack. And several of those have been corrected, but we are still waiting for some of those updates to make it to PyPI be released. And then we've also got in place sort of a proof of concept field line tracing routine. And right now this is working for the T89 model. And it uses the SciPy Runge-Kutta integrator. I did look into some of the field line tracing routines that are out there, and a lot of them seem to want fully gridded data, which is sometimes not so convenient for our use case. Doing it this way, you just use the field you calculate a field vector at a position and then use that to take the next step along the field line. And so that seems to be working. We have to do some more validation testing against the IDL results, and there's probably some tuning that we'll need to do in terms of step sizes and stopping conditions to keep things from just going off into space forever, which can happen. Then another interesting tool just within the past few months we've developed, and I was actually kind of shocked that we didn't already have this in PySpeedS or even IDL SpeedS. But on the PyHC Slack a while back, there were some questions about doing magnetic null finding. So I took that as an invitation to go ahead and implement that in PySpeedS. And so that lets you take missions like MMS or Cluster, where you have 4 or more spacecraft flying in a sort of fairly close tetrahedral formation. And then you could use the field measurements at those 4 points and estimate the gradients in each of the X, Y, and Z directions. And then from that, you could do a first order Taylor expansion and then find if there are any zeros nearby. And then you can look at the eigenvalues and eigenvectors of the gradient matrix. And that tells you some things about the topology of what the null points look like. So if you're studying magnetic reconnection, that's a very useful tool to have. It's similar, it uses a lot of the same lower level tools as the curlometer technique, which we have had implemented for a fair amount of time now for MMS, but now we can do the null finding as well. And then Sasha Drozdov is going to present a little bit more about this tomorrow, but I'll just give you a teaser. He's working on an interface to access magnetotelluric data sets. So that's like a little more geophysics, but you can do interesting things there. So I'll just show you a few examples. This is a Jupyter notebook showing the magnetic null finding. So I've got here is a plot of some cluster data, the 4 cluster probes. And then you could see, there seem to be like 0 crossings happening around the same time here. So that's looks like the constellation might have flown by or through a null, magnetic null. And so here's how we call the PySpeedS tool. You just give basically a list of the 4 field variables and then the 4 position variables. And then it goes off, does its processing, and returns a set of t-plot variables with the information you want. And what that looks like is here. So in the top panel, it basically, with this method, you always find a null, but it may or may not be real. Typically, the closer it is to the tetrahedron, the more you trust it. And so that top panel shows you how far it is from each of the cluster spacecraft. And then on the bottom panel, we have a couple of other figures of merit. And so the cutoff is around 0.4 for both of these. And below that, we tend to trust the results. And above that, we might be a little bit more skeptical about them. And then this middle panel, we've plotted some symbols on top of the null distance plot, and these tell you what kind of null we think it is. So there are these first two. There's such a thing as a type A radial or a type B radial, and then there's type A, not shown here, type A and type B spiral nulls. And all four of those are sort of have some three-dimensional structure. And then sometimes looking at certain criteria, we might decide to simplify them, like collapse them down to 2 dimensions and get a X type, type A or type B nulls, or the spiral ones simplify to O type nulls. And so you can see, sometimes the classification can change, depending on the details of the field around those points and those times. And this actually pretty well reproduces a plot from this particular paper I was working with. So it's nice to see that I'm able to reproduce those results. So this is suitable for a cluster. We have another example in this notebook for MMS, and for for helioswarm, this would be hopefully a useful tool. And for helioswarm, we have enough probes. We might even be able to do second order gradient estimation and even more interesting results. So that's something we can look forward to in the future. Here's just a little teaser for Sasha's talk tomorrow. So we have some pretty extensive networks of magnetometers, and so there is useful information to be had from them. So Sasha's working on a way to, it's both a data structure and a sort of a federated network of magnetometer sites. So Sasha, we're looking forward to seeing that tomorrow. And then future development plans in the near term, and by that I mean things that I would hope to have in place by summer school. We still have some plotting improvements we would like to make, especially doing things like orbit plots. I mean, you could do them now by extracting the data out of tplot variables and then calling matplotlib directly, but we would like to wrap those up in some routines like we have for IDL speedas. In particular, there's a tplot XY tool that'll let you take a 3D quantity and then project it onto one of the 3 available planes and then plot it. We're still trying to do some refactoring of our code. We've like a lot of our Dunder and it files have significant code in them. We don't really like that approach. We would prefer to have those exposed as their own .py files. And then we also would like to separate some of the mission-specific code from the general purpose tools. And we have some packaging issues we're working on. In particular, our relationship with the PyTplot package is a little bit confusing. So, if you happen to have heard somewhere that PySpeedas uses PyTplot, and then you think, oh, I'll just pip install PyTplot, you're not going to get the right package. We have a different branch that we're working from that's specific to matplotlib as the back end. And hopefully within the next week or so, I would like to get with Brian Harder, who maintains PyTplot, and see if we can do something a little less confusing about that. And then there were some recent updates to CDF-lib. They had a 1.0 release and a whole series. And there were some non-backward compatible changes there. And we have not completed our updates to make that compatible with greater than 1.0. So we currently have CDF-lib pinned at an upper version below 1.0. And I know that's not a nice thing to do if you want to coexist with other PyHC packages. So we're hoping to make that more compatible going forward in the near future. And then longer term development plans. We would like PySpeed to be available via Conda, and so that will we'll need a little help from our upstream package dependencies on that. There is some work in the works to support HelioCloud by letting you open CDFs directly from S3 buckets rather than having to download them to the local file system and open them as plain files. As I mentioned, we have some work to do on our field modeling, finish validating the current model implementations. We have a few additional Sigonenko models, TA15 and TA16, that we would like to implement. And then we have to finish validating the field line tracing and get that in place for other models besides T89. Let's see, we've had a few requests to make 2D particle slices a little more efficient. Right now, we're sort of, you can end up loading the same CDFs over and over because it sort of generates them time step by time step. And we would like to have a more efficient way of generating a bunch of particle slices from a time interval and make that more efficient. Of course, we want to continue our process of porting ideal SpeedS tools to Python. And what we're especially looking for there are some of the mission-specific calibration tools, like especially for Themis in ideal SpeedS, you have the ability to load level 1 data and then sort of calibrate it on the fly with some choices that may not be the default for our published level 2 data. So that is in progress. And then we would like to have a PySpeed GUI like we have for ideal SpeedS, and we would do this as a separate package that has a PySpeedS, and PySide 6 is I think our platform we're going to use for that. So we want to keep those problematic dependencies out of the core PySpeedS package. And then that would give you graphical interfaces to load data from plugins, load data from CDWeb or from Happy. And it's nice to see at a glance, what are the data sources that are available to you. And same thing for magnetic field modeling. It's nice to have all the parameters laid out and all the different models laid out for you. And the same thing for analysis tools. And that just makes it more discoverable and easy to find things that are maybe not so easy to find just reading through the documentation and learning what's there. And then there are other interactive visualizations, like there's this IC3D tool that exists in ideal SpeedS, and I believe the ERG team has ported that to Python, but this would be a natural way to make that available with PySpeedS. So this is the tool I'm talking about, IC3D. So you could take a calibrated 3D particle distribution and then make cuts through it on various planes and interactively move them through. And on top of these slices, you could see, you could plot contours. And I think they also have some volumetric visualizations. So that's and then you can sort of move them around in 3 dimensions, twist them and turn them, look at them from the direction you want to. So that's something we're looking forward to in the future. And I believe that's all I have. So I can take questions now. Let's see, I'm looking at the chat. I don't see.
I will go ahead and note that we're a little over time, and I wanted to be sure that Jeff got to present on the PySat thing. Rebecca has a question for you in the chat if you want to answer it there.
Okay.
Yeah, and if anyone else has further questions, there's always the chat, or find us on Slack.
Okay. Well, thanks very much, everybody.
Thank you, Jim. All right, last up is PySat. So Jeff Cleansing's presenting that.
Hey, everyone. Let's see if I can share my screen. Can you see this?
Sure can.
All right. So I'm going to keep this quick, hopefully. So these are kind of the updates of what's been happening since last year with PySat. One of the main bit of work that we've been doing has been sort of scrubbing over the standards and testings across the PySat ecosystem. This includes going over the documentation. We've been updating all the core packages to use PyProject.tomls and make things much more streamlined with pip. We've enhanced a lot of our GitHub Actions workflows. So now there's sort of standardized testings across Mac, Windows, and Ubuntu for all packages, as well as style checks both for the code and for the doc strings. We're testing everything against PyTest with coverall support, and we're adding in a manual workflow so we can test all of the downstream packages against the core PySat RC whenever we're releasing a new version of that. And the reason we do that is because there's sort of a core testing suite in the core package that the instrument libraries import and test the local code against. So our last version came out last May, version 3.1.0. This included a number of other things. The full changelog is incredibly long, but I put a couple of the highlights up here, which is improved support with X-Ray, as well as exporting data sets to NetCDF4. We're in the midst, like many other packages today, we're in the midst of reviewing our next release candidate, which hopefully will be done in the next week or so. This includes, we've actually expanded our unit tests quite a bit for the downstream packages, and this has resulted in a number of updates going on downstream. Currently, with the released packages, there's 158 unique data products in the system. That will probably increase this summer as we release a few more of the libraries downstream. So kind of as a quick reminder, we have this core PySat package. So this is sort of the end user API. The main use here is both downloading files from remote libraries as well as loading things by date. So you can just, if you've got data already, you can grab it. If you've got a local set of data or model runs that's not on the web, you can grab those as well and use sort of a common API to access and run against the data. But this requires a sort of a series of libraries that we have that interact with each of the data centers. These basically act as interpreters for the Cosmic dataset, the NASA dataset, Madrigal, as well as SWIPSI and some of the other sources of space weather indices. We've also got a version of PySat Madrigal that's currently under review. This has involved some refactoring of instrument supports. There's now, I think, better support going on with the Omni IMF, DST geomag data, as well as we've added slant TEC support for the GNS instruments. There's a new version of PySat Space Weather that came out a month ago. This has an improved data support for the various indices, as well as many of the other documentation updates and things we talked about earlier. The big support that I've been working on, and that'll probably continue throughout the summer, has been on the NASA interface side of things. And once we finalize the core code, we're going to shift to finalize this NASA code. A number of things that we've been improving the interface using both the CDAS-WS package and CDF-lib, so there's better support for loading in data through that. We had our own CDF package in the past. I think we're moving more and more toward using CDF-lib for everything, and probably will also maybe put in some pull requests down the line as we as we use it more. I expect we'll run into some questions and things. We've got some new instruments involving DE2 and Maven that are coming up in the future. As well as one thing I want to include is a better interface to sort of export your data to CDF for those of you who are data providers and are trying to make your own data sets that you want to upload to SPDF. The PySat missions library, this also received an update last year. This basically allows you to interface with SGP4 propagation software. So from the API is basically similar to anything if you're an end user, but now you're, instead of loading an instrument, you either give it a TLE or you give it Keplerian orbital elements and say, give me a day of data, and it will spit out a time series. Right now we have two different options. We're using the SGP4 package with Geospace Pi, which converts to lat long out. I also started testing this last version, the Skyfield package, which has an end-to-end unit conversion. Both of these are, the reason I wanted to have two is I wanted to check the math on how we're importing these. And actually both of these are at least converging to the same solution. So I find that promising. We've also added a standardized ecosystem template package that includes, if you're building new libraries or checking updates to other libraries, updates to issues and pull request templates, the action workflows, read the docs, documentation, community documents, and things like that. And that's all in its own little home on the PySat GitHub page. And then finally, one of the things is we've been kind of coming full circle. One of our early use cases was in PySat was using this to produce end user data sets for IVM data, both for the Cosmic 2 and ICON missions. And one of the reasons why PySat is sort of built this way is it needed to be flexible enough to live up to the CDAC standards as well as SPDF standards when you're exporting NetCDF data sets. Basically, you know, the simple answer for how you're building this is you import your data as a data frame or X-array. We have a meta class system that you can edit your both header level attributes and variable attributes sort of at a high end, and then it just combines all of those and spits out a file. So this last summer, I was working with the REACH team at Aerospace. REACH is a series of 32 dosimeters that's on a hosted payload, and basically helping them convert CSV files to NetCDF and getting those archived up at SPDF. That's all up on GitHub. Been talking with a couple of the CubeSat teams, including folks from Lighted and Sortie, in order to kind of generalize this code for further archival use. And maybe down the line, what I'd like to do is have a template package for, you know, particularly for these CubeSat missions that don't have a lot of funding, to help them package their data, get it up to SPDF with minimal problems. That covers it. Any questions?
Any questions for Jeff? All right. Thanks, Jeff. Lots of good PySat things happening in the background.
Thank you.
Yeah, that was a nice and quick summary.
Yeah.
Yeah, I guess I'll add, I'll probably be reaching out to some of the API folks and see if there's some things we could be doing to help streamline some of our support and coding process.
Good. All right. Well, we are officially a bit past the top of the hour, so I'll go ahead and wrap us up for today. See you guys again tomorrow, same time, same place. Again, you'll get a meeting reminder an hour before the meeting starts, and we'll be talking about NASA HCM grant things. Sean will do the science platforms coordination talks and some demos, and then we'll talk about a heliophysics software search interface. See y'all then.
Hey, Julie, a quick question about tomorrow. I don't know if you see my chat,
Yes,
but
I saw your
like,
chat.
yeah, how do we schedule there are 4 presentations in the first 30 minutes for HTM talks?
Yeah, so it'll be 15 minutes for your two presentations.
And 15 minutes for next. All right, thanks. Got it.
Thank you.